Okay, so we've just got an intuitive understanding of why L'Hopital's rule should be true. Why, if you take the limit of a ratio of two functions under sort of normal circumstances, you should be able to get evaluate that limit in terms of f prime over g prime. Okay, and the normal circumstances are basically, f and g are differentiable, g prime of x is not equal to 0 near a, and this thing is an indeterminate form. Okay, this is a slightly imprecise version because it says things like near, like I said before, the idea of near is subjective. It's a little bit different for different situations, what near enough actually is. So the way that we handle in mathematics, that sort of statement is in terms of the existence of an interval. So notice I don't talk about near in this exact statement at all. I talk about an interval. So the interval I in this statement is exactly how close is near enough. So imagine A on your number line, and we're shrinking our interval until it's small enough that all this is true. Okay? So imagine we have I, an open interval containing A. Okay? A is in the middle, there's an open interval containing A. And everywhere in that open interval, f and g are differentiable, and the derivative of g is non-zero, except possibly, actually, we can allow this at a itself. Okay, so the value of the derivative there can be equal to 0, but nowhere else nearby. Okay, that's basically what you would get in this sort of picture. I'll just sketch it real quick. So here is some axes, and here is a function with a horizontal tangent line right where it passes down through A on the x-axis. This is our g of x. Okay, so that's how you can get a derivative of 0 at A, but nowhere else nearby. Pretty common, actually. Well, not uncommon. Okay, so the three things that we need to have now to make this all work out is that this is an indeterminate form. So in this situation, we're stating 1, the limit of the numerator is equal to 0. It's an indeterminate form. So 2, the limit of the denominator is equal to 0. And 3, this thing over here on the right as a limit actually exists on its own. We get a finite value. Okay? And under all of these hypotheses, then these are true. This is true. Okay? So I should point out here, it's possible. This is something that the imprecise version doesn't make clear. It's possible for the left-hand side, the limit as x goes to a of f of x over g of x to exist, while the other limit on the right-hand side of the derivatives does not exist. D and E for short, does not exist. Okay, that's actually possible. Some of you will also recognize that, oh yeah, there are some other types of indeterminate forms. There's also an infinity over infinity indeterminate form. So what about that? Well, our exact statement can handle it too, but it gets more and more long-winded. You can't throw them all into a sloppy, imprecise statement like this. It's an indeterminate form. So there are all sorts of versions here that are possible. You can take these limits right here to be plus or minus infinity. You can replace this x approaches a everywhere with x approaches a from the left in each of them, or x approaches a from the right in each of them. You can also replace the a with an infinity. So you can replace a with a plus infinity or a minus infinity in each of these limits here. Okay, so that will all remain true. So it's still useful to know this sort of imprecise version because, yeah, That's basically what we're talking about here. Okay. So I want to use all of this stuff in an application of our L'Hopital's rule to a graphical situation. Okay, I don't want to dive right into these things. Okay, I want to think more like this. How can I understand what L'Hopital's rule is doing? So that'll be our next example.